Somewhere beyond the Milky Way, between one galaxy and the next, there is a darkness so wide that even distance begins to feel like the wrong word. No nearby star warms it. No planet crosses it in any familiar way. No glowing nebula fills it with color. To the human eye, and even to many of our most beautiful images, it looks like the blank space between the real things. But the modern universe has taught us to be careful with blank spaces. Think of the visible cosmos as a surface page. The bright stars spiral, galaxies, glowing clusters, and deep field images are the parts the universe shows most easily. They are real and they are beautiful, but they are not the whole page. Behind them, beneath them, and between them lies a hidden web that cannot be entered by ordinary sight. This is not a dark web of human secrets or hidden machines. It is older, quieter, and far larger. It is a cosmic hidden web made of dark matter, thin gas, hot plasma, faint radiation, missing ordinary matter, immense filaments, and voids so wide that entire galaxies seem like small lights along their edges. Much of it does not shine. Much of it cannot be photographed directly. And yet it helps decide where galaxies gather, where clusters grow, and how matter moves across the largest scales we can measure. For a long time, human imagination pictured galaxies as islands in an empty sea. But the deeper we look, the less empty the sea becomes. Light bends as it crosses invisible mass. Radio signals arrive slightly delayed after passing through thin plasma. X-rays reveal hot gas stretched through dark regions. Galaxy maps show that the bright islands are arranged along a vast structure whose deepest parts are almost invisible. Tonight we are going to move past the surface web of the universe and into the pages between the lights. We will follow the darkness, not as absence, but as evidence. We will ask what fills the space between galaxies, what hides there too faintly to see, and why the most empty-looking places in the cosmos may be among the most important. If the visible universe is only the surface layer, what lies beneath it? And what is the space between galaxies really made of, if it was never truly empty at all? Before we can enter the hidden web of the universe, we have to begin with the part that first captured the human eye, the surface. Imagine looking up on a clear night far from city lights, where the Milky Way appears as a pale river overhead. At first, the universe introduces itself through brightness. A star here, a planet there, a soft band of unresolved light stretching from one horizon to another. The eye gathers what it can, and the mind begins to build a picture from scattered points. For most of human history, that was the accessible universe. It was immense, sacred, mathematical, frightening, and beautiful. But it was still a surface view, because human sight is built for only a narrow range of light. We looked at the cosmos through the small doorway our eyes could open. The first page of the universe was written in visible light. When telescopes arrived, that page became richer. Stars multiplied. Nebulae appeared where the unaided eye had seen only haze. The moon became a landscape. Jupiter gained moons of its own. Saturn unfolded rings. The night sky stopped being a flat ceiling and became a place of depth. But even then, the universe still revealed itself mostly through what shone. A telescope teaches the mind that reality can hide in faintness. With a larger mirror, more light is gathered. With a longer exposure, dim objects begin to rise out of darkness. The blank places become less blank. One of the most powerful images in modern astronomy begins with a patch of sky that looks almost empty. A telescope points toward a small, dark region, holds its gaze there, and gathers light far too faint for the human eye. Slowly, the darkness fills with galaxies. Not nearby ornaments of the night, but distant systems, many of them billions of light years away. A blank patch becomes a crowded archive. Deep field images show that even where the sky seems quiet, the universe may be filled with distant structure. Every faint point, every tiny smear of light may be a galaxy. Some are seen as they were when the universe itself was younger. Some are reddened by distance. Some are distorted or faint because their light has traveled across deep time before reaching us. The lesson seems obvious. The universe is full of galaxies, but there is another lesson inside the same image. Even when deep field photographs reveal thousands of galaxies, they mostly reveal the things that shine. They show the luminous marks on the page, not the full page itself. They show where light escapes strongly enough to be gathered, stretched, filtered, recorded, and turned into an image. They do not show everything between those lights. And this is where the deeper story begins. A galaxy photograph can make the universe feel visible, but visibility is not completeness. The surface web is real, but it is not the whole web. The stars and galaxies are the glowing interface the first layer light allows us to access. Behind that interface lies a quieter system. Dark matter, shaping structure, gas, too thin to glow brightly, plasma stretched across enormous distances, and signals altered by what they pass through. The surface is so beautiful that we may mistake it for the whole. A spiral galaxy, for example, feels complete when seen in a telescope image. There is the bright central bulge, the winding arms, the bluish regions where young stars form, and the dusty lanes crossing the disk. It looks like an island with clear edges. But the visible disk is only part of the galaxy's true environment. Around it lies a larger halo, much harder to see, filled with dark matter and thin gas. Beyond that, the galaxy is not sealed off from the universe around it. It is connected to the dark. The same is true on larger scales. A galaxy cluster looks on the surface like a collection of galaxies held together in one region of space. But what binds such a cluster is not only the visible matter in those galaxies. Hot gas fills the space between them, glowing faintly in X-rays. Dark matter contributes the dominant gravitational framework. Light from more distant galaxies can be bent and distorted as it passes through the cluster's gravity. The visible galaxies are not the full structure. They are markers. This is a crucial shift in imagination. Galaxies are not randomly placed jewels scattered across nothing. Their positions are clues to something wider. If we could zoom out far enough and map not only the galaxies, but the relationships between them, their arrangement would begin to show pattern. At first, those hints are subtle. A galaxy here, another there, a cluster in one direction, a long chain in another. But when surveys map millions of galaxies across enormous volumes of space, the pattern becomes harder to ignore. The universe is not evenly sprinkled. Matter gathers, it stretches, it forms walls, threads, knots, and empty-looking regions between them. Even on the surface, the web begins to show through. This is why the visible universe is not false. Stars truly burn. Galaxies truly shine. Nebulae truly glow because atoms and dust interact with radiation in physical ways. The surface is not a lie. It is a beginning. A beginning can be honest and still incomplete. The first image of the universe tells us where matter has gathered enough to make stars, where energy is being released, and where gravity has assembled visible structures. But it does not tell us all the things that do not glow or glow too weakly, or reveal themselves only by shaping the path of something else. To enter the deeper web, we must learn to distrust a simple kind of seeing, not because seeing is useless, but because seeing is selective. Human vision evolved under daylight, moonlight, firelight, and the familiar brightness of a small planet. It was never built to sense dark matter, X-rays from cluster gas ultraviolet absorption by thin hydrogen, or the delayed arrival of radio waves passing through intergalactic plasma. Our eyes are local instruments. The cosmos is not local. Modern astronomy is of the long history of building new senses. Radio telescopes listen to wavelengths the eye cannot detect. X-ray observatories see energetic gas invisible from the ground. Infrared instruments look through dust. Spectrographs split light into hidden signatures of composition, motion, temperature, and distance. Gravitational lensing lets mass leave fingerprints in the shape of light itself. Each new sense opens another layer, and each layer weakens the old idea that empty-looking space is truly empty. When visible light fades, other forms of evidence remain. A place may be dark and still contain hot gas. It may be quiet and still be shaped by gravity. It may hold so little matter per cubic meter that any human idea of substance seems almost absurd, and yet across millions of light years, that thinness can add up to something vast. Scale changes the meaning of emptiness. This is where the visible universe begins to feel almost misleading. Not because the lights deceive us, but because they attract our attention too strongly. We naturally look at what shines. A bright galaxy seems important. A dark gap seems empty. But the universe does not rank its own contents by how easily human beings can photograph them. Brightness is not the same as importance. The surface web is both a gift and a trap. It is a gift because without light, the universe would remain inaccessible to us. Light carries history across distance. It lets the past arrive. The surface is how the cosmos first becomes knowable. But it is a trap if we imagine that what arrives brightly is all that matters. A deep field image can show thousands of galaxies and still hide the spaces between them. A cluster image can show hundreds of luminous members and still leave most of the cluster's mass invisible. A map of bright galaxies can trace a web while not fully revealing what the web is made of. The visible universe is a map with missing layers. And the missing layers are not decorative. They help explain how the map came to be. Dark matter helped pull ordinary matter into the structures where galaxies formed. Thin gas between galaxies stores part of the matter that did not become stars. Plasma in intergalactic space affects the signals passing through it. The regions between galaxies remember ancient processes of heating expansion, collapse, explosion, and exchange. They are part of the cosmic system, so hold the image of a deep field sky. A dark patch, no wider than a grain of sand, held at arm's length. A telescope staring until the blackness fills with galaxies. Each small mark, a system of stars, each system separated from the others by distances so vast that the image feels almost silent. Then look again at the dark spaces between them. Those spaces are not mistakes in the image, they are the next page of the story, the page visible light alone cannot easily read. Somewhere inside that darkness are halos, faint gas, low-density matter voids, and the first hints of a hidden architecture wider than any single galaxy. The surface has shown us the lights. Now the story moves into the pages between them. The surface has shown us the lights. Now the story moves into the spaces between them, into the dark fields around every galaxy in a deep image. These are the regions the eye passes over quickly because they do not offer a spiral arm, a bright core, a glowing nebula, or a clear shape to hold. They seem like the pauses between sentences, the margins around the text, the empty paper that lets the visible things stand apart. But in the universe, a margin can still contain history. Between one galaxy and another, distance becomes almost impossible to feel. Even the nearest large galaxy, to the Milky Way Andromeda, is more than 2 million light-years away. Light itself, moving at the fastest speed nature allows, needs more than 2 million years to cross that space. A message sent when early humans were shaping stone tools would only now be arriving. And Andromeda is close. Between more distant galaxies, the separations open wider until the mind begins to lose its ordinary sense of scale. A galaxy that looks like a small mark in a deep image may be separated from its neighbors by millions or tens of millions of light years. Clusters of galaxies may gather in one region, while between the clusters stretch spaces so vast and thin that the word distance begins to feel too small. It is tempting at that scale to call the darkness empty, not because we know it is empty, but because our minds need relief. The stars and galaxies are already too many. The distances are already too wide. The universe becomes easier to picture if the bright things are treated as the real objects and the darkness between them as a silent stage. But astronomy has slowly taught us that the stage is not passive. To enter these pages, imagine drifting outward from a galaxy. At first, the galaxy still fills the view. A spiral disk turns below like a luminous whirlpool. Star-forming regions glow along the arms. Dust lanes cut through the light. The center burns with the combined brightness of old stars. From far away, it looks complete, a finished island of matter and light. But as you move outward, the edge does not arrive cleanly. The bright disk fades. The spiral pattern weakens. The obvious stars thin into a scattered halo. The galaxy is no longer an image with a sharp boundary. It becomes a presence, a region of gravity, motion, and material that extends beyond the part that photographs most easily show. The first hidden pages are not far from the galaxy at all. A galaxy does not end where its visible disk fades. Around it lies a much larger environment, a halo that can extend far beyond the glowing structure seen in ordinary images. This halo is not a wall or a shell with a hard edge. It is a gradual thinning, a borderland, where the galaxy's influence continues after its light has become faint. In this outer region, called the circumgalactic medium, there may be thin gas ionized atoms, enriched material from old stars and matter that may one day fall inward again. It is neither fully inside the visible galaxy nor fully separate from it. It is a surrounding atmosphere on a scale far beyond any atmosphere around a planet. This borderland matters because galaxies are not sealed islands. They breathe, though not in the way living creatures breathe. They draw gas inward. They form stars. Stars die and throw material outward. Supernovae push heavy elements into surrounding space. Active black holes can drive powerful outflows. Over long times, matter can leave the bright part of a galaxy and enter the faint regions around it, where it mixes with older gas heats, cools, and becomes part of the larger environment. So even before we reach the true depth between galaxies, the idea of a clean edge begins to fail. The visible galaxy is more like a bright center inside a much larger field of influence. Its stars are the easiest layer to see. Its halo is harder. Its gas is harder still. Its dark matter is not seen directly at all, but it affects motion structure and mass. What we call a galaxy is already a layered system, partly visible and partly hidden. The pages between the lights begin at those fading edges. Imagine continuing outward. The galaxy shrinks behind you. The luminous arms become a pale disk. The halo grows thinner. The particles around you become so sparse that no human sense would recognize them as gas. Yet some of that material carries chemical traces, including heavier elements made inside stars. Even beyond the bright body of the galaxy, the darkness is not chemically blank. The galaxy has written beyond its visible page. Matter made in stars has been carried outward, perhaps by explosions, winds, or larger flows. It has entered regions that once seemed like empty dark. There it remains thinly spread, hard to detect, but no longer innocent of history. The space around a galaxy becomes an archive not of words, but of atoms. Between galaxies, the archive grows wider and harder to read. The intergalactic medium is the vast, diffuse material that lies beyond the immediate bodies of galaxies. It is not a fog one could see by shining a flashlight. It is not a cloud in any familiar sense. It is mostly extremely thin gas, often ionized, meaning electrons have been separated from atoms. In many regions, it exists as plasma, a state of matter made of charged particles. It can be so sparse that by earthly standards, it feels almost like nothing. But almost like nothing is not nothing. This difference is one of the central lessons of the whole journey. Emptiness is not an absolute feeling. It depends on scale, density, and method of seeing. A room without furniture is empty to a person. A vacuum chamber is empty compared with air. Intergalactic space is vastly emptier than anything ordinary experience can provide. Yet it still contains particles, fields, radiation, and structure. The difficulty is that our senses are trained by dense worlds. We live among solids, liquids, wind, soil, water, bodies, trees, buildings, mountains, clouds. Matter on Earth announces itself by resistance. It has weight. It can be touched, held, heard, smelled, seen. Even air, invisible most of the time, presses on us constantly. We know it exists because it moves. Leaves carries sound, fills our lungs, and becomes wind against skin. Intergalactic matter does not behave that way for us. If a human body could somehow survive there, which it could not, the matter between galaxies would not feel like air. It would not gather as fog around the face. It would not push with the presence of weather. But over millions of light years, sparse particles add up. They affect passing light. They trace structure. They reveal the large-scale history of matter. Scale turns faintness into importance. A single nearly empty cubic meter may seem meaningless, but a filament stretching across tens of millions of light years can contain enormous amounts of ordinary matter while remaining almost invisible. This is one reason the space between galaxies is difficult to understand. It is not empty enough to ignore, but it is too thin to reveal itself easily. The pages between the lights are written in faint ink. Some of those pages are shaped by voids. A cosmic void is not a perfect nothing. It is a region where matter is much less dense than in the surrounding filament's walls and clusters. Voids can be enormous, vast, dark chambers in the large-scale structure of the universe. They contain fewer galaxies, less gas, less visible material, and lower density overall. But they are still part of the cosmic pattern. A void is not the absence of the web. It is one of the web's shapes. This can be difficult to picture because the word void feels absolute. It sounds like nothingness, an open hole in reality. But in cosmology, a void is more like a deep valley in the distribution of matter. The valley is real because the surrounding ridges are real. It helps define the structure around it. The emptier-looking region is part of the same architecture as the dense knots where galaxies crowd together. In a strange way, the voids help the web become visible. If everything were evenly filled, there would be no filaments, no clusters, no walls, no contrast. Structure depends on difference. It needs dense places and sparse places, gathering and thinning knots and openings. The darkness between galaxies is not one uniform blank. It has geography. It has regions of relative richness and regions of deep quiet. There is no single kind of darkness. Some pages are near galaxies where halos hold gas, and gravity still belongs strongly to the luminous system nearby. Some pages lie between galaxies in groups and clusters where hot gas can fill the space between many galaxies at once. Some pages stretch through filaments where matter gathers along long cosmic threads. Some pages open into voids where the density drops and the silence becomes immense. Each region changes the meaning of between. Between the stars inside a galaxy is not the same as between galaxies inside a cluster. Between galaxies in a cluster is not the same as between clusters across a void. Between 2 points on the cosmic web may mean crossing hot gas, dark matter, structure, faint plasma, low-density regions, and light that has traveled for billions of years, carrying subtle signs of what it passed through. The universe becomes less like a set of islands and more like a layered map. On the first layer, there are stars and galaxies. On the second, halos around those galaxies. On the third, gas between galaxies. On the fourth, larger patterns of clusters, filaments, and voids. On deeper layers still, there is mass we cannot see directly shaping the paths along which everything gathers. To move through those layers is to move from appearance towards structure. The pages between the lights are not empty pages, they are difficult pages. They require different reading. A normal photograph reads brightness. A spectrum reads composition and motion. A radio signal can reveal free electrons along its path. X-rays can reveal hot gas. Distorted galaxy images can reveal invisible mass. Computer simulations can test whether the patterns we see could grow from small differences in the early universe under gravity's slow work. Each method opens another hidden page. But before we reach those methods, it is enough to let the central change settle. The darkness between galaxies contains the outskirts of galaxies, the thin material between them, the quieter regions of cosmic voids, and the first signs of larger structure. It is a place where matter can be faint, spread out, ionized, hot, ancient, enriched, or nearly undetectable. The mistake is not noticing darkness. The mistake is stopping there. We must allow darkness to become a question. What kind of dark is this? Is it a void, a halo, a filament, a cluster environment, an intergalactic stretch of plasma, or a path crossed by ancient light? What has passed through it? What has been thrown into it? What does it hide because it does not shine? These questions begin to pull the documentary inward. They lead us beyond the first hidden pages and towards something more fundamental. If galaxies and clusters are arranged in patterns, and if the dark spaces between them are not random, then something must help shape those patterns. Thin gas alone is not enough. Visible galaxies alone are not enough. The universe seems to have an invisible framework, a deeper layer that guides where matter gathers long before stars make the structure bright. This is where the hidden web becomes darker. Behind the galaxies, behind the faint gas, behind the pages between the lights, there is mass that does not shine at all. It does not appear as stars. It does not glow as nebulae. It does not announce itself through ordinary light. Yet without it, the visible structure of the universe becomes difficult to explain. The next page is not merely hidden, it is dark. The next page is not merely hidden, it is dark. Not dark in the ordinary sense of a room with the lights turned off, or a sky before dawn. This darkness is stranger than that. It is not simply matter waiting for light to fall upon it. It is matter that does not shine, does not glow, and does not reflect enough for our telescopes to see in the usual way. And yet without it, the visible universe does not make sense. This is the dark web behind the galaxies, not the hidden internet of human secrecy, but a cosmic dark web of invisible mass spread through and around galaxies, clusters, filaments, and the enormous spaces between them. It is not a separate place. It is a deeper layer of the same universe present wherever gravity has been quietly shaping the surface we can see. At first, this idea feels almost unreasonable. How can something be so important if it cannot be seen? Human intuition trusts light. We believe in the star because it shines. We believe in the galaxy because it leaves an image. But dark matter asks us to believe in something through consequence rather than appearance. It is known by what it does. One of the clearest clues comes from the turning of galaxies. Imagine a spiral galaxy from above its arms sweeping outward from the bright center. Stars near the middle move around the galactic core. Stars far out in the disk also move. If the visible matter were most of the mass, the outer stars should behave in a way that follows the visible distribution of that mass. But many galaxies did not behave that way. The outer stars were moving too fast. They were not flying away yet. The visible matter did not seem sufficient to hold them in those orbits. Something else had to be contributing gravity. Something extended beyond the bright disk. Something surrounded the galaxy, like an unseen halo, larger and more massive than the luminous structure that photographs make familiar. The visible galaxy was not the whole galaxy. A spiral galaxy appears to have an edge, a region where the brightness fades into the dark. But its gravitational presence extends farther. Its dark matter halo may reach far beyond the visible stars surrounding the luminous disk, with invisible mass that shapes the motion of everything within it. The galaxy then is not only a bright island, it is a bright island embedded in darkness that has weight. This is hard to picture because dark matter does not behave like the dark things we know. A black rock can be seen if light falls on it. A dark cloud may block the light behind it. Dust in space can obscure stars and glow faintly in infrared wavelengths. But dark matter is not simply ordinary matter hidden in shadow. It is not cold gas that failed to light up, or dust too faint to see, or planets too small to count. The evidence points to something different. Dark matter interacts strongly through gravity, but not through light, in the ways ordinary matter does. When we say dark matter, we mean matter whose presence is inferred mostly through gravity. It pulls. It bends light through gravitational lensing. It affects the motion of stars and galaxies. It helps determine how structures grow. It is part of the universe's deep layer, not its illuminated surface. The clue grows stronger when we move from galaxies to clusters of galaxies. A galaxy cluster is one of the largest gravitationally bound structures in the universe. It may contain hundreds or thousands of galaxies, along with hot gas spread between them, and an immense amount of unseen mass. If we measure only the stars and galaxies, the cluster does not seem massive enough to hold itself together in the way observed motions suggest. If we observe how the cluster bends the light of more distant galaxies behind it, the gravitational lensing reveals more mass than the visible galaxies alone can provide. The light is telling us where the darkness is. Picture a massive cluster between Earth and a field of far more distant galaxies. The distant galaxies send their light toward us. As that light passes near the cluster, gravity curves its path. When the light finally arrives, the background galaxies may look stretched into arcs, smeared into curves, or subtly distorted across the image. The cluster has acted like a natural lens, not made of glass, but of mass. This is one of the most beautiful reversals in astronomy. Dark matter does not shine, but it can bend the path of light. A cluster's unseen mass does not draw a visible outline, but it changes the images behind it. The lensing map becomes a kind of shadow cast by gravity, not because dark matter blocks light, but because it guides light along curved paths. It is like reading the shape of glass by watching how the view behind it warps. Gravitational lensing is especially powerful because it does not depend on whether the mass is bright. Stars, gas, dark matter, all contribute to gravity. If there is mass, it can affect light. This makes lensing one of the key ways scientists map the invisible framework of galaxy clusters and large-scale structure. But lensing alone does not tell the whole story. It reveals mass, not always substance. It can show that something massive is there, but not by itself. Explain how much of that mass is dark matter, how much is hot gas, how much is ordinary matter in galaxies, or how that matter is moving. To open the hidden web more fully, astronomy needs other searches, other traces, other ways of reading what does not shine. Still, lensing gives a crucial lesson. The surface web and the dark web are intertwined. The visible universe gives us the signals. The dark universe shapes the signals. Light travels from distant galaxies, crosses regions of invisible mass, and arrives altered. By studying the alteration, scientists infer what the light encountered on its way. The universe hides, but not perfectly. It hides enough to make seeing difficult, but not enough to erase consequence. Dark matter may not glow, but gravity is patient. It acts across distance. It gathers matter. It holds galaxies together. It draws structures toward one another. It leaves a record in motions and distortions. Where light cannot reveal the object motion and shape, can reveal the force. This is why dark matter becomes essential to the hidden web. If we only had visible galaxies, the large-scale universe would still look patterned, but the pattern would be harder to explain. Galaxies do not simply appear wherever they like. They gather along filaments and around clusters. They avoid the deepest voids. They trace a structure much larger than themselves. The visible galaxies are like bright points along an invisible frame. Dark matter is a major part of that frame. In the early universe, matter was not distributed perfectly evenly. There were tiny differences in density, small regions where gravity could begin to gather material slightly more strongly than elsewhere. Over immense time, those small differences grew. Dark matter, because it did not interact with light the way ordinary matter did, helped form gravitational structures that later guided ordinary matter. Gas fell into these gravitational wells. Stars formed. Galaxies appeared. The light came later. This is another important reversal. We often imagine the shining objects as the primary things and the darkness as what lies between them. But in the history of structure formation, the invisible framework helped prepare the places where the shining objects would eventually form. The surface page was printed on a deeper page. This does not mean dark matter does everything. Ordinary matter has its own complex physics. Gas can heat, cool, collapse, form. Stars explode and interact with radiation. Galaxy formation is a long, complicated process involving both dark matter and ordinary matter, both structure and turbulence, both gravity and heat. But without dark matter, the architecture changes profoundly. The universe we see with its galaxies, clusters, filaments, and voids depends on this unseen gravitational scaffolding. The visible structures trace it imperfectly, like lights along roads at night. The roads themselves may be hidden, but the lights reveal that something organized lies beneath their arrangement. This is where the hidden web becomes more than metaphor. A web is not just a collection of points. It is a pattern of connection. It has strands, intersections, open spaces, and tension across distance. In the cosmic web, galaxy clusters form at dense knots. Filaments stretch between them. Voids open where matter is sparse. Galaxies appear along the strands like beads or sparks bright enough to be seen, but not massive enough to explain the entire structure alone. Dark matter gives the web much of its hidden weight. We should be careful here, because dark matter is not the same thing as the gas between galaxies. Ordinary matter is made of the familiar particles that form atoms, protons, neutrons, and electrons. It can become stars, planets, gas, plasma, dust, bodies, oceans, and air. Dark matter is something else known through gravity, but not yet understood at the particle level. The mystery is still open. Scientists have strong evidence that dark matter exists, but they do not yet know exactly what it is. Many possible candidates have been proposed. Experiments have searched for dark matter particles. Observations continue to test how it behaves on different scales. The hidden web is therefore not only hidden because it is hard to see. It is hidden because its substance remains unknown. That uncertainty is part of the wonder. Science can know that something is present before it fully knows what that something is. We can infer a planet from the wobble of a star before seeing the planet directly. We can infer mass from lensing rotation and clustering. In the same way, dark matter is a name for a persistent pattern of evidence that visible matter alone does not explain. The name marks the mystery, not its solution. In a calm night sky, every visible galaxy becomes double in the mind. There is the galaxy that shines, and there is the larger gravitational shape around it. There are the stars that appear in the image, and there is the dark halo that does not. There are clusters glittering with galaxies, and there is an invisible mass distribution bending the light behind them. The universe begins to have depth behind every visible object. This depth changes the emotional meaning of the dark spaces between galaxies. They are no longer just intervals. They are regions shaped by invisible matter. A dark stretch between two clusters may be part of a filament. A void may be a region where the web thins. A galaxy may appear isolated, but its halo may reach into a larger, gravitational environment. The hidden web has gravity before it has light. And gravity is slow in the way cosmic stories are slow. It gathers over millions and billions of years. It amplifies tiny differences. It pulls matter toward denser regions. It turns slight unevenness into clusters, filaments, and walls. It empties other regions by drawing matter away from them. Over time, the universe becomes a landscape of concentration and absence, not evenly filled, but deeply patterned. Dark matter is central to that landscape. Imagine again a galaxy cluster. Instead of seeing only a swarm of galaxies, imagine the invisible mass holding and surrounding it. Imagine light from more distant galaxies passing behind it, bending slightly as it crosses the cluster's gravity. Imagine hot gas filling the space between the cluster galaxies, glowing in X-rays that ordinary eyes cannot see. Imagine the cluster not as a pile of luminous objects, but as a knot in a much larger web. The visible cluster is the surface sign. The hidden web is the deeper reality. If we could pull back farther, far beyond one galaxy, far beyond one cluster, the dark matter structure would begin to join into something larger. Strands of matter stretching across space, intersections where clusters grow wide open, voids where matter is sparse, and sheets that help define the architecture of the observable universe. At that scale, the dark web behind galaxies becomes the source of the cosmic web itself. The dark matter does not tell the whole story, but it tells us where the next story must go. Because once we understand that invisible mass helps organize galaxies, we can ask a larger question. What does the full structure look like? If the surface lights are arranged along something hidden, and if dark matter gives that arrangement its gravitational skeleton, then what is the architecture of the universe when seen at the grandest scale? That is the next page. Not just darkness behind galaxies, but the source code of the cosmic web. Not just darkness behind galaxies, but the source code of the cosmic web. To understand this layer, we have to pull back until a single galaxy becomes too small to hold the story. The Milky Way becomes one bright point among many. Nearby galaxies become a small group. Groups become clusters. Clusters become part of something larger still. Slowly, the universe begins to look less like a scattering of lights and more like a hidden pattern made visible only at enormous scale. Imagine a map beginning as darkness. At first, only a few points appear, then more. A galaxy here, another there, a crowd in one region, a long curve in another. At low resolution, the pattern may still look accidental. But as the map grows wider, as more galaxies receive distances and positions, randomness begins to weaken. The dots start to gather into chains. Chains become walls. Dense knots appear where many lines meet. Between them, enormous dark regions open. The universe begins to draw itself. This pattern is the cosmic web. It is not a web in the tidy sense of threads arranged by design. No mind drew it. No center planned it. It grew from the early universe through gravity expansion and time. Tiny differences in density became the first seeds of structure. Regions with slightly more matter pulled more strongly. Matter flowed toward them. Other regions became emptier by comparison. Over billions of years, the universe developed knots, strands, sheets, and wide-open spaces. The galaxies are the bright marks on that pattern. If we could map only a few galaxies, the web might remain invisible. A handful of lights can always look random. But when surveys map thousands, then millions of galaxies across huge volumes of space, the randomness begins to break. The galaxies are not sprinkled evenly. They gather in long chains. They crowd into clusters. They form walls and sheets. Between these dense structures are vast regions where galaxies are rare. The surface page begins to reveal its underlying layout. This is why the idea of source code is useful, as long as we keep it gentle. The cosmic web is not literally written like a program, but it does have a hidden order beneath the visible display. A deep image shows galaxies like luminous icons on a screen. A large-scale map reveals something more fundamental, the arrangement behind those icons, the invisible logic of gravity and matter that decides where the bright points appear. At the largest scales, the universe has texture. There are filaments, the long thread-like regions where galaxies and gas collect across tens or even hundreds of millions of light years. There are clusters, the dense knots where many galaxies gather inside immense gravitational wells. There are sheets and walls, broad structures of matter stretched across space. And there are voids, enormous, low-density regions that make the brighter structures around them stand out more clearly. This is the architecture hidden behind the surface view. A filament can be imagined as a cosmic bridge, but even that image is too solid. It is not a bridge of stone or steel. It is a region where the density of matter is higher than in the surrounding voids where dark matter, gas, and galaxies align along a long gravitational pathway. It may be mostly invisible, except for the galaxies that shine within it and the subtle signals that reveal its gas and mass. A cluster is different. A cluster is one of the great knots of the web. Here, many galaxies gather in the same gravitational region. The space between them can contain extremely hot gas, so hot that it emits X-rays and far more mass in dark matter than in the visible galaxies alone. A cluster is not simply a crowd of galaxies. It is a deep well in the web. Then there are voids. Voids may be the easiest part to misunderstand. Their name sounds like absence, as if they are holes cut into the universe. But a cosmic void is not absolute nothingness. It is a region where the density of matter is much lower than in the surrounding web. There may still be some galaxies, some gas, some particles, some fields, but far less than in filaments and clusters. A void is not outside the cosmic web. It is part of its shape. The web needs its empty-looking spaces. Without voids, the filaments would not stand out. Without low-density regions, there would be no contrast, no visible geography of matter. The universe would be more uniform, less structured, less legible as a web. The voids are like the dark spaces between lines in a drawing. They do not disappear from the image. They help define it. This is one of the quiet shifts in the documentary's journey. Earlier darkness looked like the absence of the story. Now it becomes part of the story's grammar. The dark regions between bright structures are not simply where the universe forgot to place galaxies. They are the negative spaces created by the same gravitational history that built the dense regions. The cosmic web is a pattern of gathering and thinning. Matter gathers into knots. It stretches into strands. It spreads into sheets. It becomes sparse in voids. Dense regions collapse and heat. Sparse regions become emptier relative to their surroundings. Galaxies form, merge, fall into clusters, or remain in quieter environments. The web is not a still diagram. It is a history in slow motion. The universe we see now is not merely a spatial arrangement. It is time made visible. A galaxy cluster is the result of billions of years of gravitational gathering. A filament is a pathway along which matter has been drawn and shaped over cosmic time. A void is a place where matter has moved away relative to denser structures. The source code of the cosmic web is written through evolution. In the early universe, matter was almost smooth, but not perfectly smooth. There were tiny variations, small differences from place to place. Those differences were extremely slight, but gravity is patient. Where matter was a little denser, gravity pulled a little more. That pulled in more matter, which made the region denser still. Over time, the tiny difference grew. The small became enormous. Dark matter played a crucial role in this growth. Because it does not interact with light in the same way ordinary matter does, it helped form gravitational structures into which ordinary matter could later fall. Gas responded to those wells. It cooled in some places, heated in others, collapsed into galaxies, streamed along filaments, and gathered in clusters. Stars and galaxies made the web visible, but the deeper pattern was prepared before the lights fully appeared. This gives the visible universe a different feeling. A galaxy is no longer only a beautiful object. It is a clue to the hidden density field beneath it. A cluster is no longer only a crowd. It is a knot where the web has tightened. A chain of galaxies is not only a coincidence. It may trace a filament, a long line of structure shaped by gravity across unimaginable distances. The lights are like labels on hidden roads, but not every road has the same brightness. Some filaments may contain many galaxies. Others may be dominated by matter too faint or diffuse to be easily seen. Some parts of the cosmic web can be traced through galaxy positions. Others require indirect methods, gravitational lensing, X-ray emission, absorption lines, radio signals, and simulations that show how structure should grow under gravity. This is why the source code is hard to read. The universe does not give us a complete map from one kind of observation. Visible light reveals one layer. Dark matter reveals itself only through gravity. Hot gas may reveal itself in X-rays. Cooler gas may leave absorption signatures in the light of distant quasars. Free electrons may slightly delay radio signals crossing intergalactic space. Each method reads a different piece of the hidden structure. No single telescope opens the entire web. Instead, modern cosmology works by layering evidence. Galaxy surveys give positions and distances. Gravitational lensing maps mass that may not shine. X-ray observatories reveal hot gas in clusters, and in some cases between clusters. Computer simulations test whether the structures observed today can grow from early density variations. Together, these methods allow scientists to reconstruct an architecture no human eye could see directly. The source code is read through its effects. This is very different from looking at a planet through a telescope. A planet has a surface. It reflects light. It has a visible disk. The cosmic web, by contrast, is too large, too faint, and too diffuse to appear as one object. It is not framed in the sky like a moon. It is the large-scale arrangement within which galaxies, clusters, and voids exist. We do not stand outside it looking in. We are inside it. The Milky Way itself is part of the web. Our galaxy belongs to a small group of galaxies, including Andromeda and many smaller companions. That group lies within a larger cosmic environment influenced by nearby structures and larger flows. Even when we imagine the cosmic web from far away, we are embedded in one of its regions, looking outward from within a single bright point along a much larger pattern. This makes the cosmic web both enormous and intimate. Enormous because its structures reach across scales that overwhelm ordinary language. Intimate because the matter in our own galaxy, our own star, our own planet, and our own bodies belongs to the same universe shaped by those structures. The web is not a distant decoration beyond the galaxies. It is the larger context in which galaxies like ours formed at all. The source code did not merely arrange the scenery, it helped make the scenery possible. If matter had remained perfectly smooth, the universe would not have formed galaxies as we know them. There would have been no dense knots for clusters, no filaments tracing the growth of structure, no rich environments where galaxies interact, no low-density voids shaping the map by contrast. The tiny early irregularities mattered because they became the seeds of everything later visible. A nearly smooth universe had to become uneven. That unevenness is not a flaw. It is the condition for complexity. Stars require gas to gather. Galaxies require matter to collapse. Clusters require gravity to concentrate mass. Even the darkness between bright objects depends on difference. Where matter gathers here, it becomes rarer there. Where a filament grows a void is defined beside it. The cosmic web is the universe learning shape, and yet the word shape can make it sound too solid. The web is not a frozen sculpture. It is more like a vast, slow-flowing structure, with matter moving under gravity, gas heating, as it falls into clusters, galaxies, traveling along filaments and voids, expanding relative to denser regions. In this sense, the source code is still running. The web is not finished. Galaxies continue to move. Clusters continue to grow. Gas continues to fall, heat cool and spread. Dark matter continues to shape gravitational wells. Light continues to cross the structure, carrying signs of what it passed through. The surface view gives us stars and galaxies. The source code gives us relation. Relation is the hidden meaning of the web. A galaxy is not only itself, it has a place in a larger pattern. It may sit inside a group near a filament, on the edge of a void, or falling toward a cluster. Its history may be shaped by gas flows, mergers, gravitational tides, and the environment around it. The cosmic web turns isolated objects into parts of a larger system. That is why the old island image begins to fade. Galaxies still look like islands in photographs, and in some ways the metaphor remains beautiful. But an island is also connected to the seabed, to currents, to weather, and to hidden geology. In the same way, a galaxy may appear alone in the dark, but it belongs to an environment shaped by mass and history. Connection does not require closeness. The cosmic web connects not by touching in the familiar sense, but by structure, gravity, shared origin, and the flow of matter across time. A galaxy cluster and a distant filament may be separated by distances that dwarf imagination, yet both belong to the same grand pattern. And still the web is physical. Its knots contain clusters. Its strands contain galaxies and gas. Its voids contain low-density regions of real space. Its dark matter bends light. Its ordinary matter leaves faint traces. Its history is recorded in the distribution of the universe itself. To understand what lies between galaxies, we must understand this geography. The space between galaxies is not one kind of space. It may be a galaxy halo, a filament, a cluster environment, a sheet, a void, or part of a larger flow. It may contain dark matter, ordinary gas-hot plasma traces of heavy elements, faint radiation, and signals passing through. But those ingredients do not float in shapeless emptiness. They belong to the cosmic web's structure. The web gives the between its meaning. Before we explore missing ordinary matter, we need to know where such matter might hide. Before we follow cosmic search engines, we need to know what they are searching through. The source code tells us that the darkness has pattern, and pattern is the first step away from nothingness. So imagine zooming out beyond the Milky Way, beyond the local group, beyond nearby clusters, beyond familiar maps. The galaxies shrink into points. The points gather into threads. The threads meet at knots. Between them, vast dark regions open. The universe begins to resemble a luminous structure suspended in blackness, but the luminosity is only the visible clue. Beneath it lies dark matter, gravity, gas, and time. The homepage has faded. The hidden architecture is beginning to load, but architecture is not substance. A structure can tell us where things are arranged, but not everything it is made of. We have seen the skeleton and the layout. Now the question becomes more physical, more intimate, and in some ways more surprising. If the cosmic web is real, what fills its strands? The next layer is not only dark matter, it is ordinary matter, but ordinary matter in a form so thin and faint that it nearly vanished from the cosmic account. Hydrogen-helium ionized gas-hot plasma and the missing baryons of the universe wait in the deep web between galaxies. If the cosmic web is real, what fills its strands? For a long time, one of the strangest answers began as an accounting problem. Cosmologists could estimate how much ordinary matter should exist, not dark matter, not dark energy, but the familiar kind of matter made of particles like protons and neutrons. Yet, when astronomers looked around the nearby universe, a large share of that ordinary matter was difficult to find. It was not all locked in stars. It was not all sitting inside bright galaxies. It was not all gathered into obvious clouds. The universe seemed to be hiding some of its most familiar substance in its least familiar places. Hydrogen-helium ionized gas-hot plasma and the missing baryons of the universe wait in the deep web between galaxies. Ordinary matter is the kind of matter we know best. It is the matter of stars, planets, oceans, dust, rocks, air bodies, and the page beneath a hand. It is the matter that can become visible, solid, warm, bright, or alive. It is the matter that makes the human world feel real. But in the space between galaxies, ordinary matter becomes almost unrecognizable. It is no longer gathered into mountains, seas, trees, clouds, or bodies. It is not even mostly gathered into stars. Much of it exists as thin gas ionized particles and plasma spread across distances so vast that any local patch may seem nearly empty. It is ordinary in its particles, but extraordinary in its condition. Familiar matter has been stretched into an unfamiliar form. To understand this, we have to separate two mysteries that are often confused. Dark matter is the invisible mass we explored earlier. It shapes galaxies and clusters through gravity, but it does not interact with light in the ordinary way. Its exact nature remains unknown. Ordinary matter, by contrast, is made of baryons, the particles that include protons and neutrons, along with electrons, forming atoms and ions. This is the matter that can form hydrogen, helium, carbon, oxygen, iron, water, stone, stars, planets, and eventually living things. The missing matter in this section is not dark matter. It is ordinary matter hiding in an unordinary place. That distinction matters because the phrase missing matter can sound as if we are speaking about the same darkness as before. But the missing baryons are a different puzzle. When cosmologists measured the early universe and calculated how much ordinary matter should exist, the numbers told a story. There should be more ordinary matter than we could easily find in stars, galaxies, and visible gas nearby. The universe had not misplaced it. Nature does not lose things for our convenience. It was missing from our observations. The matter was expected, but much of it did not show up where the eye naturally looked. It was not shining brightly as stars. It was not gathered into obvious clouds. It was not sitting conveniently inside galaxies. A large share seemed to have slipped into the deep web. This turns the space between galaxies into a cosmic accounting problem. If ordinary matter exists but does not appear in the bright places, then where has it gone? The answer increasingly points toward the thin, hot, diffuse material stretched through the cosmic web, the intergalactic medium, and especially the warm-hot intergalactic medium, often called the WIM. It is not a single cloud or a single reservoir. It is a vast, uneven presence, woven through filaments, halos, and the regions between galaxy systems. The name sounds technical, but the idea can be held gently. Warm-hot does not mean warm in the human sense. It refers to gas much hotter than anything comfortable or Earth-like, often reaching temperatures where atoms are stripped of electrons and become ionized. Intergalactic means between galaxies. Medium means the material filling that environment. So, the warm-hot intergalactic medium is in simple terms a reservoir of extremely thin, very hot ionized gas spread through the cosmic web. It is matter but not matter as we usually imagine it. A particle here, another far away, electrons separated from nuclei, hydrogen and helium transformed into plasma by heat and radiation. Traces of heavier elements drifting through space after being forged in stars and pushed outward by explosions or galactic winds. The density is so low that any small region would seem empty, but the scale is so immense that the total amount becomes important. This is the deep web of ordinary matter. It does not sit on the surface of the universe. It does not announce itself with starlight. It does not gather into clear images that a telescope can simply photograph. Instead, it must be inferred from faint signals, absorption lines, X-rays, radio delays, and the way distant light changes as it passes through. And it is not evenly spread. Some of it gathers near galaxies. Some stretches along filaments. Some fills the space between galaxies and clusters. Some lies at the edges of voids, thinning toward regions where matter is scarce. Gravity, heat expansion, and cosmic history have arranged it unevenly. It follows the same large pattern as the cosmic web, but in a faint, diffuse form. This is where the old image of galaxies as islands becomes even less complete. If galaxies are islands, then the deep web is not an empty sea. It is full of nearly invisible currents, temperatures, particles, and traces of ancient events. Matter flows toward galaxies, surrounds them, passes between them, and sometimes is pushed back out. The ocean image is imperfect, but it helps us feel that the space between galaxies has content. The content is simply too thin for our instincts. On Earth, matter seems most real when it resists us. A stone resists the hand. Water presses against the body. Air fills the lungs. Even dust can be seen when sunlight catches it. But between galaxies, matter can be so thin that no human sense could treat it as substance. It would not feel like air. It would not gather like smoke. It would not shine like a cloud. Yet it is there. The universe is not required to make its contents dense enough for touch, bright enough for sight, or loud enough for direct experience. A thing can be real and still almost vanish inside local emptiness. A region can contain matter and still seem empty at any single point. Across cosmic distances, faintness becomes measurable. The deep web is built out of scale. A single thread of gas between galaxy clusters may be too diffuse to see easily, but across millions of light years, it can contain enormous mass. A signal passing through it may be changed only slightly, but enough for careful instruments to notice. A distant quasar may send light across it, and that light may arrive with tiny missing wavelengths where atoms or ions in the gas absorbed specific energies. The matter hides, but it leaves fingerprints. This is why the missing baryon problem is such a good mystery. It is not a mystery of something completely unknowable. It is a mystery of something too spread out to see in the usual way. The numbers suggest it should exist. Simulations suggest where it should be. Observations begin to catch it in fragments. The hidden web becomes readable not as a single image, but as a collection of faint consequences. Every detection feels like opening a small hidden page, a line in a spectrum, a soft X-ray glow, a radio pulse delayed by electrons, a filament inferred between clusters, a gas bridge suggested by combined observations. None of these is as simple as pointing a telescope at a galaxy and admiring its spiral arms. The deep web does not give itself to the eye so generously. It asks for patience. It asks us to read absence carefully. The surface universe overwhelms us with beauty. Galaxies, nebulae, star fields, and clusters are visually rich. The deep web is quieter. Its wonder is not in color or shape, but in realization. Something can be almost invisible and still account for a vast part of ordinary matter. Something can look like a gap and still hold the material history of the cosmos. The darkness has substance. That substance also has origin. The simplest elements, hydrogen and helium, formed in the early universe. Later stars forged heavier elements in their cores and in explosive deaths. Over billions of years, galaxies formed stars, lost gas, gained gas, merged, erupted, and pushed material outward. Supernovae scattered heavy elements. Black holes at galactic centers released energy into their surroundings. Winds from galaxies carried enriched matter into halos and beyond. The space between galaxies became chemically marked. Intergalactic gas is not always untouched material from the beginning of time. Some of it has passed through stars. Some of it carries the ashes of stellar interiors. Some of it has been heated by collapse into filaments and clusters. Some of it has been shocked ionized and spread through the web by processes too slow and vast for daily imagination. The deep web is not only matter, it is memory. A trace of oxygen in diffuse gas may tell of stars that lived and died. A metal-enriched halo may tell of outflows from a galaxy. Hot plasma between clusters may tell of matter falling into dense structures and being heated as gravity gathers it. The ordinary matter hidden between galaxies is not a blank reservoir. It has been altered by the long history of cosmic structure. This changes the meaning of ordinary. Ordinary matter is not simple. It can burn in stars, freeze in comets, flow in oceans, form atmospheres, become living cells, or drift as ionized plasma between galaxies. Its ordinariness lies in its category, not in its behavior. The same broad family of particles can become a human hand or a nearly invisible intergalactic gas. Between galaxies, ordinary matter has been thinned almost to silence. But silence is not absence. Imagine a strand of the cosmic web stretching between two galaxy clusters. Along it, dark matter provides much of the gravitational structure. Galaxies may appear here and there, bright markers along the strand. Between them, gas lies extremely thin, heated by shocks, ionized into plasma, carrying electrons and atomic nuclei through the dark. To a human eye, the filament may seem invisible. To the universe, it is a real structure. To detect it, science must look for the ways it touches passing signals. This is why Section 5 naturally leads to Section 6. We can describe the deep web, but description alone is not enough. How can anyone claim that the space between galaxies contains this ordinary matter if the matter is so faint, so hot, so thin, and so hard to photograph? The answer is that astronomy learns to read what hidden matter does to other things. It can absorb specific colors from a background quasar. It can glow faintly in X-rays if it is hot enough and dense enough. It can scatter light from the cosmic microwave background in galaxy clusters. It can delay radio waves from distant bursts. It can bend light when mass is present, even if that mass does not shine. The invisible becomes visible through consequence. We began by asking what lies between galaxies. At first, the answer seemed to be distance, then faint halos and voids, then dark matter, then the architecture of the cosmic web. Now the answer has become more intimate. Ordinary matter itself transformed into a deep, diffuse, nearly invisible layer. The same universe that makes stars also makes silence between stars. Now we are ready to ask how this hidden layer is accessed. If most of it does not shine like a galaxy, if it does not form a clear object, if it is stretched through distances too wide for direct seeing, then the old way of looking is not enough. We need the tools that search behind the surface. To open the deep web, astronomy needs cosmic search engines. To open the deep web, astronomy needs cosmic search engines. Not search engines in the human sense, with typed words, glowing screens, and results appearing in neat rows. The universe does not arrange its hidden pages for easy browsing. It does not place labels on dark matter plasma filaments or missing baryons. It does not tell us where the invisible begins or where the visible ends. Instead, it sends signals. A beam of light crosses a cloud of gas and loses certain colors. A radio burst travels through thin plasma and arrives slightly spread out in time. Light from a distant galaxy passes near a massive cluster and bends into an arc. X-rays come from gas so hot that ordinary eyes would never see it. The cosmic microwave background passing through galaxy clusters carries tiny changes left by energetic particles along its path. These are not pictures in the simple sense. They are clues. To study the space between galaxies, scientists often cannot look directly at the thing itself. The matter is too faint, too diffuse, too hot, too spread out, or too dark. So they study what happens to other signals when those signals travel through it. The hidden web becomes readable because it leaves fingerprints on light. The universe is searched by consequence. One of the most elegant of these cosmic search tools is gravitational lensing. Mass bends the path of light. A galaxy cluster, with its visible galaxies, hot gas, and dark matter, can act like a vast natural lens. Light from more distant galaxies travels across space passes near the cluster and arrives at Earth distorted. Sometimes the distortion is dramatic. A background galaxy may appear stretched into a long arc around the cluster. Sometimes the same galaxy may appear in multiple places. More often, the effect is subtle. The shapes of many distant galaxies are slightly sheared, each one altered only a little, but together forming a pattern that reveals where invisible mass must lie. This is a beautiful form of indirect seeing. Dark matter does not glow, but it bends light. A cluster's unseen mass does not draw a visible outline, but it changes the images behind it. The lensing map becomes a kind of shadow cast by gravity, not because dark matter blocks light, but because it guides light along curved paths. It is like reading the shape of glass by watching how the view behind it warps. But lensing alone does not tell the whole story. It reveals mass, not always substance. It can show that something massive is there, but not by itself. Explain how much of that mass is dark matter, how much is hot gas, how much is ordinary matter in galaxies, or how that matter is moving. To open the hidden web more fully, astronomy needs other searches, other traces, other ways of reading what does not shine. One of those ways is absorption. Imagine a distant quasar, one of the brightest objects in the universe, powered by matter falling toward a supermassive black hole. Its light travels for billions of years before reaching us. Along the way, it passes through gas between galaxies. That gas may be almost invisible on its own, too thin to glow brightly enough for a normal image. But when quasar light passes through it, atoms and ions in the gas can absorb very specific wavelengths. When scientists split the quasar's light into a spectrum, those absorbed wavelengths appear as missing lines. The gas has written itself into the light by taking something away. This is a quiet kind of detection. There is no bright cloud to admire, no obvious shape in the sky. There is only a distant source and a subtle pattern of absence in its light. Hydrogen, oxygen, carbon, and other elements can leave signatures depending on their state temperature and ionization. From those signatures, scientists infer the presence of gas that might otherwise be completely hidden. The page is read by what is missing from the sentence. Absorption lines can reveal gas in galaxy halos, in intergalactic space, and along cosmic filaments. They can show that the space between galaxies contains not only hydrogen and helium, but also traces of heavier elements. Those heavier elements tell us that some of the gas has been touched by stars. A line in a spectrum can become a memory of ancient stars. The quasar is not the main subject anymore. It becomes a lamp shining through the hidden layers of the universe. The gas between galaxies is the nearly invisible material that changes the lamp's light before it reaches us. Astronomy learns to read the interruption. Another search tool comes from X-rays. Some gas between galaxies, especially in galaxy clusters and parts of the cosmic web, is extremely hot. Gas falling into deep gravitational wells can be heated to millions of degrees. At such temperatures, it can emit X-rays. These are not visible to human eyes, and Earth's atmosphere blocks many X-rays from space, so telescopes must observe them from above the atmosphere. In X-rays, the spaces between galaxies inside clusters can glow. This is surprising if one imagines a cluster as only a collection of galaxies. In visible light, the galaxies stand out as separate objects. But in X-ray observations, the cluster can appear filled with hot gas spread throughout the space between them. That gas may contain more ordinary matter than the stars in the galaxies themselves. The cluster is not just a crowd, it is an atmosphere on a cosmic scale. The darkness between the galaxies becomes a furnace. Filaments outside clusters are harder. Their gas is often thinner and fainter than the hot gas in dense cluster centers. Detecting it may require long observations, careful modeling, and multiple lines of evidence. But when hot gas is found stretching between clusters, it gives the cosmic web a physical presence. The filament is no longer only a pattern of galaxies or a prediction of simulation. It contains real heated matter. The hidden web becomes warm enough to leave a trace. Then there is the Sunyaev-Zeldovich effect. The universe is filled with the cosmic microwave background, ancient radiation left from an early hot phase of the cosmos. As this radiation travels through galaxy clusters, it can interact with energetic electrons in hot gas. The interaction slightly changes the energy of the microwave photons. A cluster can leave a tiny mark on the oldest light in the universe. This effect allows scientists to study hot gas in galaxy clusters and large-scale structure in a way that does not rely on visible brightness. The gas does not need to appear as a beautiful image. It alters the background radiation passing through it. The web is searched by disturbance. Perhaps the most poetic modern search tool is the fast radio burst. A fast radio burst is a brief, intense flash of radio waves from far beyond the Milky Way. Some last only milliseconds. Their origins are still an active area of research, with magnetars among the leading sources for many cases. But for the story of intergalactic space, the source is only part of the mystery. What matters here is the journey. Picture the burst, leaving a distant galaxy. It travels outward, crosses its local environment, enters the vast space between galaxies, passes through plasma halos, filaments, and thinner regions, then continues toward us. Along the way, it meets free electrons scattered through the cosmic web. Those electrons affect the radio waves. Lower frequency waves are delayed slightly more than higher frequency waves. By the time the burst reaches Earth, its signal has been dispersed, stretched in a way that carries information about the matter it passed through. A flash becomes a measuring tape. A burst that lasts less than a blink can carry a record of enormous distance. It arrives with a delay pattern that tells scientists about the electrons between its source and us. Those electrons are part of ordinary matter, often in forms too diffuse to see directly. By collecting many fast radio bursts from different directions and distances, scientists can begin to weigh the hidden ordinary matter spread through intergalactic space. The deep web leaves a time delay. This makes fast radio bursts feel almost like messages from behind the surface layer, though they are not messages in any human sense. They are natural events, crossing cosmic distances, altered by the invisible medium. They allow astronomy to ask not only where bright objects are, but what fills the path between a distant flash and a telescope on Earth. The path becomes the subject. In older imagination, the space between source and observer is just the distance light must cross. In modern cosmology, that distance contains information. The journey changes the signal. Every delay absorption bend or scattering can become evidence. The between is not empty transit. It is part of the measurement. This is how the hidden web begins to open, not all at once, not like a curtain pulled back, more like a dark page slowly illuminated from many sides. Lensing maps mass, absorption lines reveal gas, X-rays show hot plasma. The Sunyaev-Zeldovich effect marks energetic electrons in ancient microwave light. Fast radio bursts help count matter along their path. Galaxy surveys trace the visible points of the web. Simulations test whether all these pieces belong to the same growing structure. Each search engine finds a different layer, and because each method has limits, the methods must be combined. A lensing map might show where mass lies, but not the temperature of the gas. X-rays may reveal hot, dense gas, but miss cooler or more diffuse material. Absorption lines can detect gas along a narrow line of sight, but not always give a full three-dimensional picture. Fast radio bursts can estimate electron content along a path, but require many events and careful separation of different environments. The hidden web is too subtle for one key. It requires many keys. This is why scientific caution matters. When studying something faint, indirect, and spread across vast distances, it is easy to overinterpret a signal. Foreground contamination instrument limits uncertain distances, complex environments around galaxies, and model assumptions can all affect the result. A cosmic search engine must learn what not to count. This caution strengthens the story. The hidden web is believable because many kinds of evidence point toward the same large picture. Galaxies trace filaments. Lensing reveals invisible mass. Hot gas appears in clusters and some bridges. Absorption lines reveal thin gas. Radio bursts help locate ordinary matter across cosmic paths. The web is not seen by one eye, but by many senses. The eye sees darkness and says perhaps nothing is there. The spectrograph says certain wavelengths are missing. The radio telescope says this burst was delayed. The X-ray observatory says hot gas is present. The lensing map says mass is bending light. Each one answers the eye with a quieter truth. There is matter here. There is structure here. There is something in the dark. The hidden web is uncovered through patience. A small distortion here. A faint line there. A delayed pulse from a galaxy far away. A simulation compared against a survey. A cluster studied across wavelengths. A filament suggested by several forms of evidence rather than one simple picture. This is discovery as accumulation. For a sleep documentary, there is something calming in that. The universe does not need to shout. It can be read slowly. It can reveal itself through tiny differences that remain after careful checking. A hidden filament may not glow like a nebula, but it can still leave enough traces for patient instruments to find. The darkness becomes legible, and yet legibility does not mean completeness. The hidden web is still difficult. There are uncertainties in how matter is distributed, how gas heats and cools, how galaxy feedback pushes material outward, and how much ordinary matter lies in each cosmic environment. The broad picture is strong, but the details continue to sharpen. The hidden pages are not all open yet. By now, the journey has changed. We began with stars and galaxies, the bright surface of the universe. We moved into the pages between the lights, then the dark matter behind galaxies, then the source code of the cosmic web, then the deep web of ordinary matter. Now we have seen that the hidden web can be searched not directly in the familiar way, but through consequences written into passing signals. The universe can be read from the marks it leaves on light. But once the hidden web is opened, a new question appears. If this space is filled with matter, if gas and plasma stretch through it, if galaxies sit inside halos and filaments, if signals cross it and change as they travel, then the space between galaxies is not merely present. It is active. Matter does not simply sit there forever. Gas falls into galaxies. Stars and black holes push matter outward. Supernovae enrich surrounding space. Galaxy clusters heat their gas. Filaments channel slow flows. The hidden web has traffic, not in the human sense of roads and vehicles, but in the slow cosmic movement of matter across billions of years. Now that we know how to search the dark, we can ask what moves inside it. Now that we know how to search the dark, we can ask what moves inside it. The hidden web is not a frozen map. It is not a still diagram of filaments, clusters, voids, and glowing points. It is a slow system of movement, exchange heating, cooling, falling, escaping, and returning. Across spans of time, too large for human feeling matter, travels through the spaces between galaxies. This is the traffic in the dark, not traffic with roads, engines, headlights, or sound. Nothing here moves with the urgency of a city street. The motion is ancient and almost silent. Gas drifts along filaments. Galaxies fall toward clusters. Hot plasma fills the space between galaxies and dense environments. Material is pulled inward by gravity, then pushed outward by explosions, winds, and black holes. The hidden web is not empty distance, it is an exchange system. A galaxy seen from far away looks like a completed object, a spiral disk, a bright center, a halo of stars, a shape that can be named and admired. But a galaxy is not closed. It is not sealed from the space around it. It lives inside an environment, and that environment helps decide what the galaxy can become. Galaxies need gas. Without gas, there are no new stars. Stars are born when gas cools, gathers, collapses, and becomes dense enough for gravity to draw it inward toward ignition. A galaxy rich in cold gas can keep forming stars. A galaxy that loses its gas, or has it heated too much, can fade into a quieter state, filled with older stars and little new birth. So, the space around galaxies is not just background. It is a reservoir, a boundary, a source, and sometimes a barrier. Gas can fall into galaxies from their surroundings. It can arrive slowly through halos and filaments, guided by gravity, into regions where galaxies grow. Some of it may come from the wider intergalactic medium. Some of it may be recycled material gas that once belonged to the galaxy, was pushed outward and later returned. A galaxy breathes through its edges. This breathing is not regular or gentle, like a sleeping body. It is uneven, enormous, and shaped by violent events. Stars form in dense clouds. Then the most massive stars live short lives and die in supernova explosions. Those explosions send energy and material back into surrounding space. They heat gas stir it, enrich it with heavy elements, and sometimes push it out of the galaxy's visible disk. Imagine one of those outflows from far outside the galaxy. The spiral disk glows below, but from its star-forming regions, heated gas is being driven outward. It carries atoms forged inside stars, oxygen, carbon, silicon, iron. Some of this material may remain in the halo. Some may mix with other gas. Some may fall back later. Some may travel farther than the bright galaxy itself, entering the dim environment around it. Matter that was once deep inside a star can be thrown into the dark around a galaxy. That thought changes the emptiness again. The space outside a galaxy may contain atoms forged in stellar cores. Oxygen, carbon, silicon, iron, and other heavier elements can be carried outward by stellar death and galactic winds. They enter the circumgalactic medium, the broad halo-like region around a galaxy, where the boundary between galaxy and intergalactic space becomes blurred. The dark around galaxies is not chemically innocent. It has been touched by stars. The gas around galaxies is not just leftover material from the early universe. Some of it is enriched, marked by the life and death of stars. Some has been heated by supernovae. Some has been pushed by radiation and winds. Some may later cool and fall inward again, becoming part of a new generation of stars. The hidden web carries memory and motion. Black holes can also affect this traffic. At the centers of many galaxies lie supermassive black holes. When material falls toward them, it can release enormous energy. In some galaxies, especially active ones, this energy can drive powerful outflows, heat surrounding gas, and influence whether gas cools enough to form stars. This process is often called feedback. The word sounds modest, but the idea is large. A galaxy forms stars. Stars and black holes release energy. That energy affects the gas. The gas then affects future star formation. The system responds to itself. It does not grow in one simple direction. It regulates, interrupts heats, expels cools, and sometimes begins again. In this way, galaxies and their surroundings are locked in conversation. The conversation is written in gas. If gas cools and falls inward, the galaxy may brighten with new stars. If gas is heated or expelled, star formation may slow. If the surrounding halo retains gas, the galaxy may have fuel for the future. If the galaxy falls into a cluster, its gas may be stripped, heated, or cut off from fresh supply. Environment matters. Inside galaxy clusters, the traffic becomes more intense in a different way. A cluster is a dense knot of the cosmic web, a region where many galaxies share a deep gravitational well. The space between those galaxies is filled with extremely hot gas known as the intracluster medium. It can reach temperatures of millions of degrees, glowing in X-rays rather than visible light. In ordinary photographs, a cluster may look like a crowded field of galaxies, but in X-rays, the space between them becomes the dominant presence. The dark is filled with heat. Now picture a galaxy falling into such a cluster. Its stars may continue moving together, but its gas is more vulnerable. As the galaxy travels through the hot intracluster medium, pressure from that thin but energetic environment can strip gas from it. Trails may form behind the galaxy. Its supply of star-forming material can weaken. Over time, a galaxy that once formed many new stars may become quieter. The environment reaches into the galaxy. At cluster scales, traffic is not only matter flowing in and out, it is galaxies themselves moving through crowded gravitational space. They fall inward, they orbit, they interact. They may merge, be stretched, disturbed, or stripped. The cluster becomes a place where the hidden web accelerates change. Yet even outside clusters, the movement continues more quietly. Along filaments, matter may stream toward denser knots. Gas can be drawn by gravity into larger structures. Small galaxies and groups can follow the same pathways, slowly joining clusters over time. The filament becomes a kind of cosmic route, not a road in the human sense, but a region where matter is more likely to travel because gravity has shaped the path. This is why the word traffic matters. The hidden web has direction. Matter is not evenly wandering through a blank universe. It is responding to structure. Dense regions pull, filaments guide. Voids become comparatively sparse as matter gathers elsewhere. The cosmic web is a map of where movement has happened and where movement continues. The traffic is slow, but it is not meaningless. A cloud of gas falling into a galaxy may one day become stars. Gas expelled by supernovae may enrich a halo. Plasma between clusters may reveal where matter has been heated by gravitational collapse. Metals found far from galaxies may tell of ancient outflows. A radio signal delayed by free electrons may cross regions where ordinary matter is spread too thin to see. Every movement leaves a trace somewhere. Sometimes the traffic is outward. A galaxy forms many massive stars, and those stars explode. Their energy pushes gas beyond the star-forming regions, perhaps even beyond the visible disk. In active galaxies, jets and winds from a central black hole may drive material farther still. The galaxy sends part of itself into the dark. Sometimes the traffic is inward. Gas cools, condenses, and falls back. Material from the circumgalactic medium feeds the galaxy. Streams from the cosmic web supply fresh fuel. A galaxy that seemed isolated may actually be drawing from a wider environment, quietly taking in matter from beyond its luminous body. Sometimes the traffic is circular. Matter can linger cool and return. It can be changed by the journey. It may leave enriched with heavy elements, mix with more primitive gas, then re-enter a galaxy in a new form. The boundary between inside and outside becomes less like a wall and more like a breathing surface. The hidden web recycles. This recycling is one reason galaxies are difficult to understand as isolated objects. A galaxy's color-shaped star formation and future depend not only on its internal structure, but also on what happens around it. Does it live in a rich cluster or a quieter field? Is it near a filament? Is it receiving gas? Is it losing gas? Has feedback heated its surroundings? The answer may lie in the dark around it. This makes the space between galaxies feel more active than the word space suggests. We often use space as if it means separation. But in cosmology, the space between galaxies can be part of their relationship. It can contain the gas they exchange, the gravity that links their motion, the plasma that records their history, and the paths through which matter travels. The between is not only distance, it is process. That process has been unfolding for billions of years. The early universe produced hydrogen and helium. Gravity gathered matter into the first structures. Stars formed and changed the chemistry of the cosmos. Galaxies grew through gas accretion mergers and feedback. Clusters heated gas to enormous temperatures. Filaments carried matter through the web. Voids became the quieter chambers of the large-scale universe. The traffic in the dark is the motion of that history continuing. It is tempting to imagine that once galaxies form, the main story is inside them. Stars are born there. Planets form there. Life, at least on Earth, appears inside one galaxy around one star. The glowing parts feel like the centers of meaning. But the hidden web reminds us that galaxies are not alone in their own making. They are shaped by inflow, outflow stripping, heating, cooling, and surrounding structure. The universe makes galaxies through connection. Even a quiet galaxy contains evidence of this larger exchange. Its stars hold chemical histories. Its halo may contain gas enriched by earlier generations. Its movement may reflect the gravitational pull of nearby structures. Its future may depend on whether gas continues to arrive from the surrounding web or whether its fuel has been cut off. A galaxy is not only a collection of stars, it is a chapter in a larger circulation of matter. This circulation does not happen smoothly everywhere. Some galaxies are rich in star-forming gas. Some have become red and quiet. Some are transformed by clusters. Some are disturbed by mergers. Some sit near filaments where matter supply may continue. Some drift in sparse regions where change is slower. The hidden web does not treat every galaxy the same. Environment matters. There are always local details. A galaxy's mass history, black hole mergers, gas supply, and surroundings all matter. But the cosmic web provides the wider stage, and more than that, the wider system. It helps determine where matter can gather, where gas can flow, where clusters grow, and where galaxies may be starved or fed. The traffic in the dark is therefore both grand and delicate. Grand because it spans millions of light years. Delicate because its traces can be faint, a missing absorption line, a soft X-ray glow, a trail of stripped gas, a change in star formation, a delayed radio pulse. The movements themselves may be enormous, but our access to them is often subtle. We read a vast flow through small signs. There is a calm wonder in that. Between galaxies, where the eye expects silence, matter is moving through a deep and ancient circulation. It does not hurry. It does not need to be visible to be real. It travels through halos, filaments, clusters, and low-density regions. It carries heat particles, metals, and memory. The hidden web is not only structure, it is motion. A star belongs to a galaxy. A galaxy belongs to a halo. A halo belongs to an environment. An environment belongs to the cosmic web. Gas moves across these boundaries. Energy crosses them. Gravity connects them. Light passes through them and returns changed. The deeper we look, the more boundaries soften. The universe is not static furniture arranged in a dark room. It is a slow exchange of matter through structure. As this section closes, imagine again the visible universe as the surface page. The stars are bright words. The galaxies are luminous paragraphs. The clusters are bold marks in the text. But beneath and between them, the hidden web carries the traffic that makes the page alive with history. The page is still being written. The space between galaxies is no longer a blank. It has structure. It has matter. It has hidden mass. It has plasma. It has signals. It has flow. It has history. It is not crowded in the human sense, not dense, not warm, not breathable, not alive in the biological sense. But it is active in the cosmic sense, shaped by gravity and filled with slow consequences. The final step is to gather these layers into one changed image of the universe. Not a universe of isolated lights floating in nothing, but a universe whose darkness is part of its architecture. Not a homepage of bright galaxies alone, but a hidden web where the quietest regions may hold the deepest clues. The universe was never empty. The universe was never empty. It only looked that way from the surface, from Earth, and even from many of our most beautiful images. The cosmos first appears as a story of lights and darkness. Stars shine. Galaxies glow. Clusters gather like distant cities. Around them, between them, and behind them, blackness seems to stretch without content. The mind naturally treats that blackness as the space where nothing happens. But the journey has changed that image. The darkness between galaxies is no longer a simple blank. It is a hidden web of structure, gravity, thin matter, plasma signals, motion, and ancient history. It is not full in the way a room is full. It is not dense in the way a cloud is dense. It is not warm or breathable or close to anything human life can touch. But it is not nothing. The visible universe is only the surface layer. It gives us the stars, galaxies, nebulae, and clusters that first teach us to look outward. That surface is real and beautiful, but it is incomplete. Behind it lies dark matter, shaping where galaxies gather. Through it runs ordinary matter in strange, diffuse forms, hydrogen, helium, ionized gas, and hot plasma, spread across distances so large that faintness becomes part of the structure. And through that hidden layer, light itself travels changed. A distant galaxy can appear distorted because invisible mass has bent its light. A quasar can lose certain colors because gas between galaxies has absorbed them. A fast radio burst can arrive slightly spread out in time because free electrons have delayed some frequencies more than others. The cosmic microwave background can carry tiny marks from the hot gas it passed through. The hidden web does not need to shine brightly to be read. It leaves consequences. At the beginning, space between galaxies seemed like a distance. Now it feels like a record. It holds traces of gravity's long work of matter, drawn into filaments of gas, heated in clusters of stars that died and sent heavier elements outward, of black holes that changed their surroundings, of signals crossing regions too thin for sight but not too thin for measurement. And darkness becomes an archive. The voids, too, are no longer pure absence. They are the quietest regions of the cosmic pattern, the low-density spaces that help define the web around them. A void is not a hole outside the universe. It is a valley in the distribution of matter. It is emptier than the filaments and clusters, but it still belongs to the same architecture. Even nothingness has become more precise. This is the strange discipline of modern astronomy. It does not let the eye decide too quickly. It asks what kind of darkness we are seeing. It asks whether the space is near a galaxy halo, inside a cluster, along a filament, or deep in a void. It asks what particles might be there, what signals have passed through, what mass might be bending light, what gas might be too hot or too thin for ordinary images. The universe has taught us that visibility is not the same as reality. Human perception is drawn to surfaces. We notice what shines, what moves quickly, what has shape, color, edge, and drama. The rest becomes background. But the cosmos does not organize itself around human attention. Some of its most important structures are slow, faint, diffuse, invisible, or indirect. The quiet layers matter. Dark matter does not shine, yet it helps shape the large-scale universe. Intergalactic plasma does not appear like a bright cloud, yet it holds a share of ordinary matter. Voids may look empty, yet they help define the cosmic web. A faint delay in a radio pulse may carry evidence from millions or billions of light years of hidden material. Again and again, the background becomes part of the story. This does not mean every region of space is crowded. It is important to keep the wonder honest. Intergalactic space is unimaginably empty by any earthly standard. It is far thinner than air, far thinner than mist, far thinner than the best vacuum most people can imagine. If we could place a human sense inside it, that sense would not feel substance. It would feel absence. But cosmic meaning does not always live at the scale of the human hand. Across millions of light years, even a few particles per vast volume can matter. Across the length of a filament-thin gas can become a large reservoir. Across the path of a radio burst, free electrons can leave a measurable delay. Across a cluster-hot plasma can become one of the dominant forms of ordinary matter. Across the universe, faint structure becomes the pattern of everything. Scale changes emptiness into architecture. This is why the old image of galaxies as lonely islands is no longer enough. The galaxies are still separated by enormous distances. Their isolation is real in one sense. Light may need millions of years to travel from one to another. Any imagined journey between them would cross a darkness so wide that ordinary language begins to fail. But isolation is not the same as disconnection. Galaxies sit in halos. Halos sit in environments. Environments belong to filaments, sheets, clusters, and voids. Gas moves in and out. Gravity links motion across scale. Matter gathers along pathways prepared long before stars began to shine. The visible islands are part of a hidden geography. The universe is connected without being close. That idea lets us hold two truths at once. The cosmos is vast beyond comfort, and yet it is not random emptiness. It is sparse but structured, dark but not blank, thin but not meaningless, distant but connected by gravity, matter, radiation, and time. The hidden web is the shape of that connection. It is also a reminder that the universe is older than our categories. We divide things into object and space matter, and emptiness, foreground, and background. These divisions help us think, but the cosmos often softens them. A galaxy does not end cleanly at the edge of its light. Its halo extends outward. Its gas can move beyond the visible disk. Its history can be written in material far outside its bright body. The boundary between galaxy and intergalactic space is not a wall. It is a transition. In the same way, the boundary between seeing and knowing has changed. Astronomy no longer depends only on direct images, though images remain precious. It reads spectra, delays, distortions, faint emissions, maps, simulations, and statistical patterns. It learns to see what does not shine by studying what the hidden thing does to what does shine. The hidden web is opened indirectly, one clue at a time. There is humility in this. We do not stand outside the universe with a complete view. We are inside one galaxy, around one star, on one small planet, using instruments to gather fragments of a structure too large to see all at once. Every map is partial. Every method has limits. Every answer sharpens some questions and leaves others waiting. But partial does not mean powerless. From our small location, we have learned that galaxies trace larger structures. We have learned that dark matter shapes the web through gravity. We have learned that ordinary matter can hide in diffuse gas and plasma. We have learned that signals crossing the dark can reveal what the dark contains. We have learned that voids are not simply nothing, but part of the universe's large-scale form. The surface has opened into depth. The hidden pages were always there. We only needed better ways to read them. When we return now to a deep field image, it no longer looks the same. The thousands of galaxies are still magnificent, but the darkness around them has changed. It is no longer merely the part of the picture where nothing appears. It is where the next question lives. What halos surround those galaxies? What gas stretches between them? What dark matter binds their larger pattern? What voids open around their filaments? What faint signals have crossed that space on their way to us? The blackness has become active in the imagination. It has become a place where the universe keeps its quieter records. The real revelation is not that space is secretly crowded like a city. It is not. The revelation is gentler and stranger. Even the emptiest-looking regions can have structure, content, and history. Even what seems blank can become meaningful when the scale is large enough, and the instruments are patient enough. The universe is not full in a human way. It is full in a cosmic way, full of relationships, full of gradients, full of traces. full of old radiation crossing new structures, full of particles spread almost beyond imagining, full of gravity acting where light is absent, full of matter so thin it nearly escapes our instincts, yet so vast it reshapes the inventory of the cosmos. This is what the space between galaxies is really made of, not simply stars, because most of it is not star-filled, not simply darkness, because darkness is not a substance, not simply emptiness, because particles, plasma fields, radiation, and mass remain, not simply dark matter, because ordinary matter also hides there, not simply gas because the gas belongs to a larger architecture. It is made of layers, visible light at the surface, dark matter behind the galaxies, filaments and voids forming the cosmic structure, diffuse ordinary matter stretched through the deep web, signals moving through it and carrying its fingerprints, slow traffic of gas heat metals and gravity across cosmic time. The between is made of connection, and now the title of emptiness begins to loosen. It was never completely wrong, but it was always incomplete. The space between galaxies is empty compared with anything close to Earth. It is empty compared with a planet, a cloud, a room, a breath. But compared with true nothing, it is rich with consequence. True nothing does not bend light. True nothing does not delay radio waves. True nothing does not absorb quasar light, hold plasma, trace filaments, surround galaxies, or shape where matter gathers over billions of years. The space between galaxies does all of these things. So, when we imagine the universe now, we can imagine it differently. Not as bright islands scattered in a dead sea, but as a hidden web whose lights are only the most visible nodes. The darkness is not a failure of the picture. It is part of the picture. It is the layer that asks for deeper tools, slower thought, and a willingness to listen for what cannot be seen directly. The night sky becomes less empty and more mysterious, not more crowded in a noisy way, but more connected in a quiet one. Somewhere between galaxies, a photon crosses a region of thin plasma. Somewhere else, gas drifts along a filament toward a cluster. Somewhere, a void widens in the large-scale pattern. Somewhere, dark matter holds a structure that no ordinary telescope can photograph. Somewhere, the faint trace of an ancient star's death lives far outside the bright galaxy that once contained it. And from a small planet inside one galaxy, we learn to read these signs. What remains is not a crowded universe, but a deeper one. A universe where darkness can have form, where distance can carry evidence, where the faintest signals can open the largest structures, where the spaces between galaxies are not merely what separates the lights, but part of how the lights came to be arranged at all. The universe was never empty. It was only waiting for us to learn how to read the dark. By the end of this journey, the darkness between galaxies no longer feels like a simple blank. It has become stranger, quieter, and more alive with meaning. What once looked like empty distance has turned into structure, invisible, dark matter, thin plasma, hidden, ordinary matter, faint signals, immense filaments, and slow movement through spaces too large for the mind to easily hold. The visible universe is still beautiful. The galaxies still shine like islands in the deep. But now those islands no longer seem alone. They sit along hidden threads inside a vast cosmic web whose deepest layers are not reached by ordinary sight, but by patient signals, careful measurements, and the long work of learning how to see what does not shine. Perhaps that is one of the gentlest lessons of modern astronomy. The universe does not reveal itself all at once. It gives us the bright surface first, then the shadow behind it, then the faint trace, the delayed radio pulse, the bent light, the missing matter, the structure that was there before we had the tools to recognize it. And so, The space between galaxies is not simply a place where nothing happens, it is part of the architecture of everything. It is where the cosmic web stretches quietly through the dark, carrying the history of matter, gravity, heat, and motion across billions of years. The next time you imagine the universe, perhaps the blackness will feel different. Not empty, not silent in the simple sense, but like a hidden page still being opened one signal at a time.